Okay, there we go. I'm a man of my word. No class on Friday.
You make you cancel too?
How about this? How about this one too?
Nice. You're one of a kind.
No homework over break. No class on Friday. All the homework is graded other than 5-1. 5-2 was due today. How was the column analysis homework?
That's alright. Not bad.
Not bad?
Nah, I got a little confused on which A value I'm using first.
That's probably like the only thing that was confusing. Hopefully that was the only thing that was confusing. And that's okay. Like we can work that out. Okay. I'll leave this up for a second for everybody who walked in after 9 o'clock.
Not Braden. Barney. Not Braden, yeah. Woo!
I didn't say anything.
I did.
All right, everybody good? Everybody good? Okay. Forgive me, my voice is still a little shot, but we'll muscle through it. Okay. So I hope everybody brought their manual today because we're going to use them. Okay. Today what we're going to do is we're going to go back to column analysis. And we're going to do it a different way. Okay. Today's lecture is really all about this table. Okay. Because this table bridges column analysis and column design. Okay, so I kind of want to explain that, but the first thing I want to do is just make sure that we are all clear with our procedure and our policy from last time. Okay, so here's how this works. Okay, so first off, we have our effective length factors. Remember, we use the recommended ones, not the theoretical ones. We have our analysis, but this is our analysis method using method 1. Or in other words, we're just raw calculating the capacity, okay? This will work every time, okay? The problem is this expression is too complicated to solve for like an area for the purposes of design. It's too complex, okay? So as a result, we need another way of analyzing columns, okay? Or we need a design tool, I guess is a better way of saying it. Sorry. We need a design tool, but we can use that design tool to analyze. So I kind of want to introduce that today, okay? So the way that method 2 works is using table 4.1. Now we're going to use 4.1a because that's for 50 KSI. Nothing changes if you have a higher grade, just a different table. Okay? What we're going to do is we're going to determine the largest KLX and the largest KLY for a column. Now, if KLY is bigger, just look it up. If KLX is bigger, what we do is we compare KLY and KL effective and look up the capacity based on the bigger of the two. And between these, we will most likely need to do some interpolation. So break out linear interpolation for that. Okay. So I kind of want to show you how this works, and I want to show you this on a 14 by 90. Okay? So, by the way, we already did this problem. Okay? We did this problem, and we got a capacity of, I think, 958. So the capacity here is going to be, should be the same. And it will be plus or minus some decimal points because of rounding and because of the interpolation. Okay? So this is what we got last time. Let's just sort of recap. So this is the problem. Remember on the y-axis, we can say that this is the biggest segment, that we can just consider y2 because it has the longest length and the highest k value. So what is KL going to be for the y-axis, by the way? So we have a k value of 1 and a length of 15. So KLY is going to be 15 feet. KLX is going to be 0.8 times 35, okay? So we're going to have to do something with that. Now, this is how we did this using method 1. In method 1, we got 958 kips. So let's see how this works. All right, let me take my keyboard off. What happened? I didn't do anything. I didn't do anything.
Just put on the mistake counter.
I think it's your fault. I'm blaming you.
I'm putting 2 on the mistake counter for that.
But I'm the one that keeps track of them.
Yeah, but you said it's my fault.
I deny that. Okay, method 2. All right. So let's just recap. What is 0.8 times 35? What is that? 28? $28. I left all my calculations upstairs, so we're doing it live. Okay. And KLY is 15 feet. Okay. So KLX is bigger. Okay. So what that means is that we're going to need to determine a KL effective. Okay. Now, just so everybody remembers, in order to do this, we divide KLX by this ratio of RX over RY. Can anybody tell me what that is for a W14 by 90? Where do we find that? We find it in table 4.1, okay? So we're going to go to table 4.1a. You're not going to find it in table 1 because table 1, you're just going to find the individual quantities. So again, today is table 4.1a land. Trust me, you're going to want to have it open. So, can anybody tell me what page we need to be on? 4-16. Okay. So, Mr. Horton, for a W14 by 90, what is the RX over RY ratio going to be? It's going to be near the bottom. And the W14 by 90 is right over there on the right, so
1.66.
1.66. Is there anybody that doesn't see that? Okay, so here's the table 4.1a, here's the 14 by 90, and it's all the way down here. Everybody good? See, the idea is we cannot directly compare KLX to KLY because it's apples and oranges, because when you compute slenderness, you're dividing by different radii of gyration. So in order to compare apples to apples, we're going to compare KLY with KL effective, okay? So what do we get here? 16.8. Give me one more.
16.86. 16.87.
16.87. Second? Okay. So what we're going to do is compare these two. So this is going to be our weak axis length, and this is going to be our strong axis length. So looking at these two numbers, and remembering that this effective length leads to slenderness, which axis governs for this column, the strong axis or the weak axis? And remember, what do I mean when I say governs? Like, remember, as slenderness increases, what happens to capacity?
Decreases.
So if I'm trying to analyze this column, what's the worst case scenario? The longer KL or the smaller KL?
Longer.
The longer, right? So which one's longer? Right here. So the strong axis governs. Is that what we found before? I mean, how did we do this before? Before, we looked at KL over R's, right? Which one had the highest KL over R? The x-axis, right? So it's the same pattern, okay? It's not like the column's going to suddenly change the way it behaves because we're analyzing it differently. The column is the column, okay? Does that make sense? Now, can somebody tell me in the table what is the capacity for 16.87 feet? That's a trick question, by the way. You can't do that, right? Because the table does not list a capacity for 16.87 feet, does it? Instead, what it does is it says we have this, and we have that. So, what do we get for these? What is the capacity when the effective length is 16 feet when it's 17 feet?
979, 955.
Right? Does everybody see that? So what we're trying to find that. I'm going to do better than that. That's what we're trying to find. We're trying to find the capacity at 16.87 feet. Y'all remember how to do this? So, let's see. Let's see if y'all remember this. So, I mean, y'all see what I'm doing? Because I'm basically saying I'm just doing linear interpolation. That's all I'm doing here. Okay? Bringing it back to those engineering computation days. So what do we get linearly interpolating? I mean, y'all see what I'm doing, right? I'm basically saying this is what I'm doing. All right, hold on. But I mean, that's basically what I'm doing, is I'm just doing that. Okay, say it again.
958.12.
We'll say 958.1. Just keep it simple. Second, what did we get before?
958.
And so we got 958.1. Where's the difference come from? Just rounding and the interpolation. I mean, the column curve looks like this, and we're linearly interpolating. Right? And again, all we're doing is this, right? All we're doing is we're saying, okay, here's a straight line fit. Here, I'll erase all these. This is getting cluttered. So at 16 feet, this is the capacity. At 17 feet, this is the capacity. We're trying to find the capacity right here. That's it, 16.87. So we're just going here and going there, and we're reading this. That's all we're doing. Right? Does that make sense? Okay. Anybody have any questions on this? Everybody good? Okay. All right. I want you to be comfortable with this process because we're going to do it, and we're going to do it a number of times. Okay. Now let's have some fun. Let's get into the world of design. Okay? What I want to be able to do is to design columns. Now, let's go back to basics. In this class, what do I mean when I say design? If I'm selecting a shape to resist a load, what has been my core tenet from day one? Let me ask it this way. If I had to choose between a W12 by 35 and a W12 by 30, which do I choose?
30.
Why?
Economically.
Exactly. So I want the lightest shape. Everybody agree? So ultimately what I want to define is a procedure that will get me that. And the truth is that unfortunately the math is hard, okay? The math associated with column equations is not as straightforward as it is for tension members. Like for example, with tension members, we just had this, right? But for columns, we have, it's a little more difficult to just solve for area when this term right here is that. Like, it's too complicated. Like, there's too much going on. We can't just solve. That's where the design aid comes into play. So this is how column design is going to work. Okay, so what are we going to do? Step one, determine the factored load. I mean, that makes sense, right? What about step two? Step two, we are going to determine the largest KLX and KLY for a given column. Now, what we're then going to do is we're going to use this. Okay? We're going to use this to select a group of trial sections. Okay? And I'll get to that here in a bit. But what's most important is that we are going to use KLY to pick these. Why? Because that's how the table's written, right? Table is written based on the capacity with respect to the least radius of gyration, with respect to RY. So we are going to select a group of trials based on KLY. Now, what do I mean by a group of trials? I want you to pick at least one W14, at least one W12, at least one W10, and at least one W8. And let me qualify that statement. It is possible that under some loads, like you might find that there are no W8s that work. That's fine, okay? That's okay. But I want you to target to try and pick one W14, one W12, one W10, and one W8, okay? So for each of these, we then need to check them. What do I mean by check them? Well, I am choosing based off of the weak axis. What about the strong axis? Well, if KLX is smaller than KLY, the problem's done. Just pick the lightest one, move on. But if KLX is bigger, for each one of these trial shapes, we need to, we need to check the strong axis and see if it's going to work or not. And then from this group of trials, select the lightest. So it's possible that we pick like 4 trial sections and maybe only 2 of them work once we check the strong axis. Once we get the lightest one, we're going to verify its capacity. And we're going to verify it using method 1, computing it using the equations. Now, I'm throwing a lot at you, and the best way to absorb it is with some practice, okay? So we're going to do one example today, one example when we get back from break. And maybe we'll try and dip our toes into that example today to kind of illustrate how it works. Okay? All right. So let's see where we get with this. Okay? Okay. Okay. We're going to select the lightest W-shaped column that we can find to resist a dead load of 100 kips and a live load of 200 kips. And the bracing is going to correspond to what we see right here. Okay? So I am going to help you out with a couple things. We're going to call this a K value of 0.65 because it's fixed. We're going to call this K of 1 and a K of 0.8. Okay. All right, so let's see what we can do. So what's our first step going to be before we do anything, like anything with the column?
Background load.
Of course, yeah. And what do we get for this? Do I have a second? Am I good there? Okay, I'm going to put that on the board just so that like we all have it visually up here. Okay. Now let's look at step 2. We need to determine KLX, KLY. KLX is pretty easy because there's only one segment. What do we get for this?
13.65.
13.65. Here, I'm just taking that. Why am I taking that? Longer segment, higher K value, right? No reason to use this one. So what do we get here? This is pretty easy. 14 feet. I'm going to space that out a little bit. Okay. So okay. So what can you tell me about this column regardless of which shape that we pick? Is the weak axis going to govern its capacity or the strong axis? The weak axis, right? Because Rx is always bigger than Ry for W shapes, right? So because of what we've got going on here, for this problem, I should say for this problem. Does that make sense? Because, I mean, take KL X divided by a number, take KLY divided by a number, but make sure this number's bigger. This ratio will always be bigger than that one. Does that make sense? So, what that means is whenever we look up a shape, it's going to work. That's what that means. So let's do this. Okay. Now, to be clear, the purpose of this example problem is to get you familiar with this table. Okay? The next example is going to be a little bit more comprehensive, but let's get familiar with this. So here's how this is going to work. Okay. If you go through table 4.1, you will find only W14s, W12s, W10s, and W8s. Remember, we only list those because for columns, those are the most efficient column sections because they're the most square. Okay? So for each of these, I want to find the lightest one possible. So what am I looking for? I'm going to be looking on the 14-foot row, and I'm going to find the lightest W14 that I can that has a capacity of at least this. So let's start with the W14s. So everybody, I want you to start going through table 4.1a, go through the W14s first, and let's see if we can find the lightest shape possible that will resist this load. And I'll give everybody a sec. I want to see what they find. And I know maybe your first time, you may not know what you're looking for. So let's see if somebody can find the first shape, and then we'll talk about it. Does anybody have a W14 that they think will work?
61.
A 61. Okay. Now, let's talk about why you picked that. What is its capacity at that intersection?
571.
571. So I guess if you're having a difficulty with this, the first thing I would ask is, are you able to find that value? At a KL of 14 feet for a W14 by 61, can you see the 571? Does everybody see that? If you don't, that's fine. Tell me. Okay. Now, let's just reason through this. Does the W14 by 61 have enough capacity to resist that load? Yes, right? Because the load is 440. The capacity is 571. Now, what is the next lightest shape next to the W14 by 61? Is it W14 by 53? What is its capacity at 14 feet? 401. Will it work? No. So from the W14s, that is the lightest shape that will work. Does that make sense? If that makes sense, find me the W12. You got one? 53. And why did you select that? What is its capacity?
512.
Okay. Okay. Is everybody else able to find that? Now, if it was between these two shapes, which would you pick? The W12. Why the W12?
It's small.
It's small. It's lighter, right? Less hit on the wallet, right? Okay. What about the W10? Buy me a W10. 54?
W10 by 49. 49.
Hold on. I'm getting the 49 too.
Yeah, the capacity is 449.
Oh, yeah.
Sorry, 471.
471. Okay. What about the W8s?
58.
And which one? Or sorry, what's the capacity? I mean,
482.
482. Does everybody notice that there's only one page full of W8s? So it's very possible that if the loads get really, really high, that we aren't going to find one. Like, for example, if the load was 640 instead of 440, are there any W8s that work? Really?
Not at 14 feet.
What's that?
Oh, yeah.
Not at 14 feet.
Yeah.
Like if the length was 14 feet, but the load was 640 instead of 440, there are no W8s that work. And that's okay, right? We would just find a W14, a W12, and a W10, okay? So I want to be crystal clear that it is possible that you just don't have a W8 that works. You might not even have a W10 that works if the loads get really high. That's okay. Now, let's make sure that we're clear on the following two questions. The first question, for this problem, do we need to check the strong axis for any one of these shapes? No, because of this, right? KLX is smaller than KLY, so no need to check any of these. So from these, we just pick the lightest one. So what's our answer for this problem?
58 by 58.
Hold on. I'm going to use that. The lightest. Lightest means less money. We're paying per pound. Yeah. I will go through the process later online probably of analyzing this if you would like me to, but I mean, how do we analyze it? We take the gross area, the RX, the RY, and just do everything we did in our last example. So I'm not going to worry with that. Instead, actually, you know what? Let's go ahead. Let's just do that real quick just to verify, just to make sure we're comfortable with this. So step 4, not needed. And that's because well, let's just verify, make sure we did everything right. Okay. So for W10 by 49, I've got that its area is 14.4. I've got that its RY what's its RX? And somebody give me its RX. It's not going to be in table 4.1. You're going to have to look it up in the front. Say it again.
4.35.
So the first thing I'm going to do is compute KL over R in the x-axis. Notice what I did here. I just used this because we already computed KL. No reason to redo the math. Okay? And then for KL over R in the y-axis, all right, so what do we get for these? Let's talk about the x-axis first and then the y-axis.
37.66.
Say it again.
37.66.
All right, what about the bottom one?
66.14.
So, which one governs?
The bottom.
Bottom. And, I mean, we predicted that. We predicted that over here without even doing this, right? We knew that was going to happen. So what's the next thing that we calculate if we want to analyze using method 1?
FE.
FE. What's E?
29,000.
There we go. Ah. So what do we get for this?
65.43.
Do I have a second? I don't have my calcs on me, so weird. I have no idea if this is right or not. Good? I heard a yeah. Okay. So what do we get here? And why am I doing this, by the way?
For elastic and inelastic.
To figure out which equation for if n based on elastic or inelastic buckling. That's right. And so what do we get here? It should be pretty big, like 100 something. 130, yeah. So that means that we're in the exponent land. That means we're doing this. And by the way, when you're in design mode and you pick a column and then you're checking it, if you don't get this, you're probably doing something wrong. Like, that's another reason why I think it's a good idea to do this. So what do we get for this? $36.31. Is that what you got? Do I have a second? Okay. What was phi again? Okay. What do we get for VPN? So we'll call it 470.6. Is that fair? What was the capacity according to method 2? $471. I mean, that's our capacity right here, right? 471. And when we did the math, we got 470.6. So this was verifying that the column that we selected does indeed actually work, which I do think is important. Look how much load these columns are holding up. That's 440,000 pounds. I think it's worth a couple minutes of calcs to make sure that it works. Okay? Now, I will say though that checking this was a formality. In other words, this capacity in this table is computed assuming the weak axis governs. The moment that we got to this step right here and we found that the weak axis governed, like I would have gone and bought a lottery ticket based on the bet that the capacity came out to 471 because that's what's listed right here, okay? The real value in doing this last step is when the strong axis governs. And that's going to become clear when we come back from break because there's going to be a lot of like checking and rechecking and interpolation. And so it really is kind of worth it to just, when you get a shape, just analyze it to make sure that it works, okay? And all I'll say about that is just sort of trust me when you come back from break. Does that make sense? Okay, now, so for the assignment, what I'm going to do is give you the same problem that you had on the last homework, same problem, but now analyze it using method 2, not method 1, okay? And then the next thing I'm going to do is I'm going to give you this problem. This is a pin-pin column, and I want you to select the lightest shape. And for this, you don't have to worry about method 1 if you don't want to, okay? You have the same bracing condition in both directions, okay? This is, again, really meant to be practice with this. Sound good? Turn this in by Friday, 9 a.m. You are free from this class until we come back from break. You okay with that? I am going to stop the recording, pull up the code one more time. Hey, take it easy. Relax. Margaritas and Mai Tais, right? Have a good break, everybody.